Okay, so we're going to investigate this kind of as a demonstration today. Inertia in car crashes. Our objective: investigate and describe the effects of inertia. First of all, what is inertia? Inertia is that idea that is the first law of Newton's law. An object at rest stays in rest. An object in motion will stay in motion unless acted upon. So whatever it's doing is going to keep doing unless it's acted upon by another force. All right, so the first one says, procedures. Use the clay to make a small figure of a person. Place the car on a flat table. Place the clay person in the car. So let me pull up my camera so you can see what we're doing here. I'm going to get our, you cannot see the camera. Okay, so our first instruction, we have two cars. Okay, we used to have army men, but we use clay. I'm not actually going to make a person out of my clay. I am just going to make a kind of blob. Okay, don't be offended. But here's my clay, little arms, I guess, person. All right. I'm going to try to make about the same size clay blob for the other car so that we can have a little bit of a comparison. I know what you're thinking. Are you serious? Yup, I'm serious. Okay. So place the car on the flat table. All right, so we have them sitting on the flat surface of the desk. Important, do not press the figure down so that it sticks. Just let it rest on the car. On your data page, record any forces that are acting on the car and person as it sits on the table. Describe the motion. Does Newton's first law apply here? All right, so what we're going to do, we're watching our little cars here, and we're going to come down to our data page for the resting car. Okay? The first thing it says to draw the forces that are acting. If this is our resting car, pretty not cool car there, but we are going to draw the forces. If it is sitting still like it shows in the video, in the camera, okay, not moving, what is one force that's acting on it? Well, there's the force of gravity, which maybe I should use a different color because that's hard to see. But okay. So if this is the force here, this would be the force of gravity. Any other forces that are acting upon the car? In your bell ringer, we talked about a force that opposes gravity. So what force opposes gravity? The normal force. That's what we had from the bell ringer, right? So we don't want to forget that normal force that we had. So the normal force. And then we're going to answer the questions for that part. Identify the forces that are acting upon the resting car. We just did. So you need to type them. Both gravity and the normal force are acting on the car that is sitting still. Okay. Now this one seems pretty at Mr. Obvious moment, but provide a description of the motion of the resting car. Still in the same place. So it's still. And then the part of Newton's first law that applies to the resting car. I'll let you think about that for a second, and then we'll discuss. So let's think. The part of Newton's first law that applies to the resting car. If we go back to our lesson today, it says an object at rest stays at rest, and an object in motion stays in motion with the same speed and same direction unless acted upon by an unbalanced force. So if these little cars are just sitting there, still sitting there, which part applies? The object at rest. So you would write the object at rest and will remain at rest unless acted upon an unbalanced force. Okay. I'll give you a couple of seconds to fill that in. So then we're going to go on to rolling car. Kind of gives us a picture here, but let's go back to our instructions for this part. It says place one end of the ramp on the stack of books or the edge of a chair to create an incline. Okay. Make sure there is plenty of room at the base of the ramp for the car to roll. Okay. Using Newton's first law, predict what will happen when the car rolls down the ramp and record this on your worksheet. Okay. So let's set that up. Okay, we probably should use it over there, but I mean, we are going to have our books, and we'll put the camera up there so that you can kind of see what we're trying to do here. Okay. I'm not stuck with it. All right, so here's our stack of books. Here's our ramps. Okay. Maybe those books are too high. Here's our ramps. All right, we're going to employ a little bit of tape so that our ramp doesn't fall down. Some of you might recognize these as Hot Wheels tracks. Okay. Oh. So what was our instruction? It said place one end of the ramp on a stack of books. We have that right here. Create an incline. Make sure there's plenty of room. Using Newton's first law, predict what will happen. Like you know what is going to happen, right? Put the car on the track. What's going to happen? At the bottom of the track, is the car going to stop or keep going? Okay, let's find out. Yep, went all the way across my desk. So we can even try that one again. Now notice, I'm just going to pick this up and show our little clay man stayed in the car. Okay, let's try the bigger one. See if we have the same results. Okay. Well, that didn't work like I thought it would. Why do you think this one stopped? Let's investigate the bottom of it. Maybe if we turn our tracks over and try it again. Maybe there was too much holding up. Let's see. These tracks must not work. I think we're going to call that one defective and stick with the one that fits in the track. All right. So I know this seems a little bit lame, but it's way more fun when you're actually doing it. All right, so using Newton's first law of predict, let's go down and answer the questions for a rolling car. I predict that when the car rolls down the ramp, it will whatever you said. After the car rolled down the ramp, what happened? So we look at our camera again. So the car rolled down the ramp. It kept going. That's all you have to write. So these are definitely things that you have seen before. Now this part. Newton's first law applies to this rolling car because if I look at the first law, an object at rest stays at rest, and an object in motion stays in motion with the same speed and the same direction, unless acted upon by an unbalanced force. So, and an object in motion. And it says, and the same speed. Let's kind of look at our car here and see, do you think it's going the same speed? Surely didn't seem to slow down in any way, shape, or form. Okay. So you should have those questions answered. And then we'll go on to the next one in about 30 seconds. All right, let's see. The next one says soft impact. So let's find our instructions for soft impact. Place a wadded up piece of paper at the end of the ramp. All right. Making sure it is in the path of the car. Using Newton's first law, predict what will happen when the car. Let the car go down the ramp and measure the distance the person is thrown from the paper wad. Okay, so we're keeping our little clay person in there. Okay. Let the car compare. Compare the direction of the car's motion with the direction of the passenger. All right. So let's look. Here is our paper wad. This is what they're going to run into. Now, what do you predict? This is a paper wad. This is a car. Is the paper wad going to stop the car? Like, this has some pretty real implications, especially those of you that are going to start driving pretty soon. We're going to put it right at the end of the ramp. Okay. And make your prediction. Write your prediction down. Do you think our little person's going to stay in the seat? Or do you think our little person's going to get thrown when it hits the paper wad? Stay in the seat? Okay, let's find out. Okay, you could kind of see what happened. The car went all the way across my seat. Just picking it up, our little person stayed in the car. Okay, so let's go ahead and answer our questions on that one. Rolling car, soft impact. So you should have written your prediction down. When the car hit the paper, the car and the passenger continued moving, right? Now, do you think that he slowed down? Let's look at our camera and see just a little bit. Maybe we'll have a little bit more of the desk on there. Watch and see if you think he slows down at all. You can just use kind of a subjective sort of opinion there. You think he slowed down? I don't think he did, but all right. So the passenger was not thrown. So it was 0 centimeters on that one, and 0. It didn't get thrown. Then how does this direction compare with the direction the car was moving? Well, it didn't get thrown. So those are all the things that you would put there. Think about, what does a soft impact look like if you were the passenger, if you were the one. But go ahead and answer those questions, and then we'll get to the other part. Say that again. The direction of the thrown person. So if our little clay person is right here, make sure he's not stuck in there or anything, and he hits the paper wad. Okay, I'm going to move my hand, but he hits the paper wad. Well, the person jiggled around a little bit, but he wasn't thrown anywhere. So at the end of the ramp, if the car kept going this way and the person flew out, then we would say the direction was different. But he stayed in the car, so he didn't have, let's see what happens when he hits the Play-Doh box. See that? It stopped the car, and the guy jiggled around a bunch. But when he hit the paper wad, which, like I said, he just kept going. And the guy stayed in there and just moved around a little bit. So it's just what direction. We're going to see in the car crash one, it's going to ask you kind of the same question, a little bit of the same questions. We're going to think through that. But this time we're going to have a little bit more things to crash into. Okay. So it says book. So we're going to come up to the instructions and see what we're supposed to do. It says replace the paper wad with a heavy object, such as a book. So we have our other two books here. Okay, and I don't have the camera up there. But roll the car down the ramp, measure the distance the passenger is thrown from the car. And so we need, I do have a ruler over here, but the passenger hasn't been thrown from the car yet. So we will see if he gets thrown from the car this time. Okay. And then repeat the experiment by using a rubber band to act as a seatbelt for the passenger. Okay. I'm going to go from the ramp. Just wait, you don't have a camera on there. Now, it stopped the car. Our little clay person did not actually come out. Oh, did you see him jump? Let's change this around just a little bit and see if we can make the guy come out of the car. Because it seems to think we should be measuring a distance that he is. So this time we're going to increase the incline. We're going to have the car hit the same one and see what happens. Ah! Okay, so the distance the guy was thrown that time was about 3 inches or about 7.5 centimeters. That's pretty crazy. Yeah. That's 7 centimeters. So we increase the incline. Let's see if we move the book back a little bit. We'll put our little person back in there. And this person got thrown more like 9.5 centimeters that time. So a greater distance this way. It had more momentum going. I'll do that again. You can see the guy. He got thrown 10 centimeters that time. So, all right. So you can see. Let's look and see what our questions were on that one. I predict that when the car hits the book, it will, whatever you predicted. What distance did the passenger travel? The greatest distance we got was 9 centimeters. Okay, on our book crash. This crash was different from the paper wide crash because why? Like, a harder impact, all right? And when you say taller, if this is the height of the paper wad, wait, you cannot see that, the camera isn't on. If this is the height of the paper wad and the thickness of the book, yeah, from that perspective, I'm sure. But what is true about this book versus this paper wad? Bigger weight, okay, it has a greater mass, so therefore it has a greater weight. The paper wad, yep, because if we hold these two, the car actually has a greater mass than the paper wad. So the car, with its mass and its acceleration, its momentum, it's going to push the paper wad away. But with the book, much greater mass, it can't push the book away. So this greater mass of the book is an important part of this. Okay. Also, let's just for interest's sake, let's say we had a much smaller person. Okay, let's take our person's mass and take it in half. Okay, see if they fly farther. Let's measure that. It's the same distance. It's about the same distance. Why is that? Because the person originally was twice as big. Of the same gravity. Okay. We'll think about that as we move along. Sure. Alright. How does the wearing... Okay, so... Then it says, how does wearing a seatbelt change the effect of Newton's first law? So we look at Newton's first law, and we say, all right, an object in motion... And you cannot see that, the camera isn't on. An object in motion is going to stay in motion unless acted upon by another force. When I let go of the car, the person kept moving. They were not acted upon by the same force. So how do you think wearing a seatbelt is going to change, which we will use tape for our seatbelt, but how does wearing a seatbelt change what happens to you in a car crash? Well, hopefully with our little seatbelt on, the person stayed in the car. Why?
He's not following the force of the car is.
Right, the seatbelt makes him become more a part of the car. So his mass is not separate, but part of the car. So it was acted upon by that same stop. Okay. This is usually one that's a lot of fun, but we couldn't share things. All right, so now we have some questions to think about on our own. It says, if you were Isaac Newton, how would you explain the first law to a fourth grader? So you guys are smart people. Fourth graders haven't really talked about the first law, first Newton's law. So what would you say to them to explain what we just looked at? Okay. I want you to go ahead and answer those 4 questions on your own, and then we'll watch the video that's in the lesson, because number 4 says, watch the video provided by your teacher. Explain what happens in terms of Newton's first law. We'll watch that in about 5 minutes. Okay.